Today we are going to be taking a look at finding limits algebraically. So we're going to look at finding limits algebraically, approaching a constant, and then after vacation we'll finish up these notes and find limits approaching infinity or negative infinity. So the first option we have here to find the limits approaching a constant is with direct substitution. So we'll substitute in that constant right into our function for x, as long as it doesn't make that denominator 0. We want to look out for any domain restrictions where the graph may have a vertical asymptote or what's called a removable discontinuity, which would be a hole in our graph. And we'll talk more about that removable discontinuity when we look at graphs of rational functions. A function is continuous at a constant c if the limit as x approaches c of f of x equals f of c. So we talked about that in the last class. This was our rule for continuity. If a function isn't continuous, it's discontinuous. We have three types of discontinuity, either asymptotic, which means there's an asymptote, a point, or a jump. So a point meaning that there may not be a value at a certain point, and then a jump meaning that maybe the left and right hand limits are going to two different values. Underneath that, as a reminder, I put our three conditions for continuity. So our limit needs to exist, f of c needs to exist, and that limit needs to equal the value at f of c. So in this first example, we have the limit as x approaches 3 of the square root of x plus 1. This is one of those instances where I could do some direct substitution and plug 3 right into my function for x. And so I get 2. For example 2, you can see I have a limit of a quotient, so we just need the quotient theorem for limits, which just basically means that if I have a limit of a quotient here, I can break apart that limit or that quotient so that we are taking the limit as x approaches 3 of the numerator, and the limit as x approaches 3 of the denominator. And then I'll do direct substitution into both. So we'll have the square root of 3 plus 1 over 3 squared minus 1. So this would be 2, like we got in example 1, and then we have 8. So my answer is 1/4. So you can see this limit, this quotient theorem for limits below. So the limit of f of x and the limit of g of x both exist, and the limit of g of x does not equal 0, then we can break apart this limit of two different functions into the limit of the numerator over the limit of the denominator. And I have some techniques for evaluating a limit of a quotient like that. And so if possible, we're going to use that quotient theorem and do some direct substitution. If the limit of f of x equals 0, so the numerator, and the limit of g of x equals 0, so the denominator equals 0, what we're going to look to do is factor those f of x and g of x and see if we can reduce. If f of x or g of x involves a square root, we might try rationalizing with the conjugate. That isn't necessarily always rationalizing a denominator by the conjugate. I might also have to rationalize with the numerator. And then if the limit of f of x does not equal 0, so the numerator doesn't equal 0, but the denominator does, then one of the following is true. Either the limit doesn't exist, or it's going to infinity or negative infinity. Now, if all else fails, we'll just set up a limit chart like we did the other day when we found limits numerically and evaluate it really close to the constant. So 2 or 3 decimals leading up to that constant and after, so that we can see the left and right hand limits. So starting off with these two, the first one we just have the limit as x approaches -2 of 2x minus 3. So no quotient happening here. So I can just go in and do direct substitution. And that's going to give me -7. On number 2, we want to check to make sure the denominator doesn't equal 0. So if I were to plug in 4, it does not equal 0, so that we can use the quotient theorem. And I'll just do direct substitution into the numerator and into the denominator. So that's going to give us 18 over 2, so we get 9. Now we just have the examples up top, so we're not going to look at the part down bottom yet because that is approaching infinity and negative infinity. So on example 3, you can see that if I were to plug that into the denominator, we would get a denominator of 0. So what we're going to do, we have a denominator that equals 0, so what we're going to do, we're going to look to factor first. So I'm going to have the limit as x approaches -3 of x plus 3, x plus 2 over x plus 3. And I'm going to reduce here. And we'll talk about what happens when we reduce in just a moment. So what we're left with then is the limit as x approaches -3 of x plus 2. And then I can do direct substitution. So -3 plus 2 would be -1. So let's take a look. What ended up happening here when you reduce out is we are creating what's called a removable discontinuity. So that will result in a hole in the graph when we eventually start graphing these rational functions. In number 4, I have a similar situation. I can't do direct substitution into that denominator as is because it will result in a denominator of 0. So what I'm going to do is factor. So the numerator will become x plus 3, x minus 1, and the denominator is x plus 1, x minus 1. So again, we have this removable discontinuity. So I'll reduce out the 1, and we'll be left with the limit as x approaches 1 of x plus 3 over x plus 1. And you want to keep this limit notation carried along until you do that direct substitution. So 1 plus 3 over 1 plus 1. So that's going to give me 2. On number 5, I can't do direct substitution. So what I'm going to try on this one is rationalizing. So I'm going to rationalize with the conjugate 1 plus root 1 plus x. I know we're used to rationalizing with a denominator to get a radical out of the denominator, but actually in this case it's going to be helpful to have it in the denominator. So we have the limit as x approaches 0, and then in the numerator it would multiply out to be 1 minus 1 plus x, and in the denominator we have x and 1 plus root 1 plus x. So in the numerator, we end up with a negative x, and in the denominator we have that x and 1 plus root 1 plus x. So these x's will reduce out for us. So we're just left with the limit as x approaches 0 of negative 1 over 1 plus root 1 plus x. And then once we get it down to here, I can do direct substitution. So negative 1 over 1 plus root 1 plus 0. So that will give me negative 1/2. With number 6, I'm looking just for a left-hand limit, and I can't do direct substitution because that will give me a denominator of 0. There's nothing to factor, there's no radicals to rationalize, so what we're going to have to do is use a table. So I only want a left-hand limit, so we know that if I plug in negative or positive 2, it's going to be undefined. So I'm going to plug in, let's do 1.9, 1.99, and 1.999. So this would give me negative 10, negative 100, and negative 1000. So we said when that denominator is 0 but the numerator isn't, we are going to either end up with a limit not existing, that it's going to infinity, or negative infinity. And in this case, it's going to end up going to negative infinity. We can see that these are just adding a 0 on the end, so we are going to go to negative infinity on this limit. When we take a look at example 7, I can see that, again, I would get a denominator of 0 if I were to do direct substitution. On this one, we can do a little bit of factoring, so I'm going to factor out a GCF of 5 in the numerator. In the denominator is this difference of 2 squares, so I get x plus 2x minus 2. So there the x plus 2's cancel, and I'm left with the limit as x approaches 2 of 5 over x minus 2. So still, I'm stuck with having a denominator of 0 if I do direct substitution. So on this one, I'm going to have to use a table. There's nothing left to factor, there's nothing else to rationalize, so we use a table. This time, 2 is going to have to be in the middle. So in the last one, we only had a left-hand limit. So this one, I have to find a left and a right-hand limit. Sorry, that should not say 2. So my left-hand limit will do 1.9, 1.99, 1.999. And then for my right-hand limit, we'll do 2.1, 2.01, 2.001. So over here, the 1.9, that gives me negative 50, negative 500, and negative 5,000. So it's looking like my left-hand limit is going to be negative infinity. And then for my right hand, I have 50, 500, 5,000. So this side is going to positive infinity. So on the left, we have negative infinity. On the right, we have positive infinity. So that means my limit does not exist. And finally, our last one here, again, nothing is going to factor, nothing is reducing, and if I did direct substitution, it would give me a denominator of 0. In this case, I only want my right-hand limit, so when I go to use a table, I know that 1 is undefined, but I'll be plugging in probably 1.1, 1.01, and 1.001. So this is going to give me 10, 100, and 1000. So it's looking like I'm going to positive infinity. So my limit here is positive infinity.